In this video, I'll calculate sample standard deviations for each of the data sets and also create a relative frequency histogram for each data set. Calculating a sample standard deviation by a table requires that we have a column for x. A column for x bar can be useful. And then we'll subtract x minus x bar in order to get the deviation of each data piece. Now in this method, we like to repeat as many 4s as there are in the data set, so everybody's included. There are 5 4s, so list them all. The mean of the data can be calculated. That's found by just adding up and dividing by 5. So our mean is 4. Let's put that down. Now the mean just gets repeated in every row. Now we subtract straight across. So 4 minus 4 makes 0. 4 minus 4 makes 0. And we just keep going like that. This is actually an easy one to do. It's easy because all the deviations are 0. Now what we need to do is we need to create a new column. And this column is for the squares of the deviations. So we take that result that we got here and multiply it by itself. But of course, 0 times itself is just 0. And so the squares of all the deviations will be 0. Our last step is to actually sum the last column. In math, the big sigma here, Greek letter, says to add up all the squares of the deviations. So 0 plus 0 plus 0 plus 0 plus 0. And it makes a total of 0. Now we're ready to plug it into the standard deviation formula. Now there's 2 standard deviation formulas. There's one for sample standard deviation and one for population standard deviation. We're going to treat this one as if it was a sample taken from a population. So I'm going to use the formula S equals the square root of the sum of the squares divided by n minus 1. That's the full standard deviation formula. The reason the table is required, though, is because of the sum, the sigma that's in it. Alright, so in a minute we'll plug in and we'll get our result. Before we do, though, let's create a relative frequency histogram for this data. So in a relative frequency histogram, we're actually going to put our x values on the horizontal axis. Now the x value is the response that you get from whatever it is that you're sampling. So if you ask people a question that's a numerical type of response, if they say their response is 4, for example, that's an x value. And so here, all the responses were 4s, but let's list different things that could have been said when we asked them the statistics question. They could have said 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and other things too. But we didn't get any other responses. We just got 4 as a response. Now on the vertical axis, we have what is called relative frequency, which tells us the percent of the data who answered in a certain way. So since everybody answered with a 4, that means there's only going to be one bar here. And the height of the bar is going to be 100%. Now we'll center the bar around the 4. We can shade it in if we like. And there we go. That's our relative frequency histogram. Okay. Notice that there is no spread to the data. It's not spread out at all. It's all concentrated in one narrow bar. So let's see what kind of standard deviation we get for this histogram. I have to plug in place of the sigma x minus x bar squared. We have to put in what we got from the table. So put that on top. Then we have to do over n minus 1. So n here is the number of data pieces that were collected. So we can clearly see that n is 5. So let's plug that in. Not surprisingly, the sample standard deviation here is 0. That was an easy one to start with. Let's try one that has some spread to the data. 2, 3, 4, 5, and 6. I'm just going to create the same table as before. We need x, x bar, x minus x bar, and x minus x bar squared. Let's list all our data pieces. And the mean of this data set, maybe you can tell by symmetry here, the mean is going to be 4. So put a 4 in every row. Now we'll subtract. 2 minus 4 makes negative 2. 3 minus 4 makes negative 1. 4 minus 4 would be 0. And 5 minus 4 is 1, and 6 minus 4 is 2. If we were to sum those up, they would actually cancel each other out because some of them are negative and some are positive. But once we square them, their sum will actually have meaning. So negative 2 times itself would be 4. Negative 1 times itself is 1 because a negative times a negative makes a positive. 0 squared is 0, 1 squared is 1, and 2 squared is 4. Now we can sum up the column. Four plus 1 plus 1 plus 4 will make 10. Alright, so we're going to plug in, use the same formula as before. We're going to want a 10 on top and an n minus 1 on bottom. That'll be 5 minus 1. Now before we calculate that value, let's go ahead and make a relative frequency histogram out of this data. So this time it's a little different. There's not going to be just one bar. We're going to have 5 different responses, so we're going to have 5 bars here. There'll be a bar for 2, a bar for 3, bar for 4, bar for 5, and a bar for 6. Now, we want to center each bar around the number that it represents, but we don't know how tall yet to make the bars, right? So now we got to figure out how tall to make them. Now, each data piece represents a certain percentage of the data, and we need to figure out how much. In order to do that, you figure out how many 2's there are. So there is just 1 2, and there's 5 data pieces. So we have to turn that into a percent. The way we do it is we take the 1 and divide by 5, and that makes 0.2. 0.2 represents 20%. Every data piece here represents 20% of the data. So that's how high we're going to want to make our bars. And they all have the same height. 2 represents 20% of the data. 3 is 20% of the data. 4 represents 20%, 5 represents 20%, and 6, 20% as well. What does it add up to? Yeah, it's up to 100%. That's all the data. The point is, when we do a histogram, we want 100% to be represented always. Let's calculate our standard deviation. Does it look like there's a standard deviation here that's non-zero? I hope so. Yeah, the data is spread out. So let's calculate it. Okay, I get 1.58. Which is a larger standard deviation than the above. Now what I'm going to show next is a way to calculate the percentages using a table. To do this, we're going to use what's called a frequency distribution. In a frequency distribution, you write down the different things that people respond to the question with, and then the frequency represents how many times those things were said. So our data was 2, 3, 4, 5, and 6, right? So those are the different responses, and we want to list them all. Now what we put in the frequency column is how many times they appear. So the 2 was mentioned once, the 2 appears once, 3 appears once, 4 appears once, 5 appears once, and 6 also appears once. They all appear an equal number of times. Now we'll find what is called the relative frequency for each. Relative frequency has a formula. It is F over N. We need to know how many times the 2 occurred and divide it by the total number of data pieces. So that's going to be 1 over 5, right? Because N is 5. N is 5 for this data set. N is 5 for this data set. Now we can get a decimal out of that. It's 0.2. But to change the decimal into a percentage, multiply by 100. Now the 3, it appeared one time. F is 1, N is 5. So again, it's 20%. They all have a relative frequency of 20%. I bring up this method, though, for finding the percentages because it could be useful in the next problem where there's repetitions of responses. Okay, so now that we know how to do a frequency distribution, let's try it for our next data set. We've got 1 0, 2 3s, 3 4s, 2 5s, and 1 8. I'll copy that data down here. Okay, so in this table, we're going to want to put a 0, a 3, a 4, 5, and an 8. Notice that in a frequency distribution, we actually don't include the repetitions. Because the repetitions are counted in the frequency column. You're supposed to say how many times they appear in the data set. So 0 appeared once. 3 appeared twice. 4 appears 3 times. There's 2 5s and 1 8. So there wouldn't be any point in repeating the entries in the X column in this particular type of table. Now, let's count up how many data pieces there are in this data set. In this data set, there are 9 total entries. So when we divide our frequencies by n, we need to divide by 9. This is going to be 0.11, which is 11%. We'll have 2 out of 9. 0.22, 22%. And we'll keep going like that. All right, now we know how high to make our bars. We need a bar at 0, and it has to have a height of 11%. There's also a bar at 8 with that same height. We should have a bar at 3 with a height of 22%. And a bar at 5 with that same height. And our tallest bar of all is the 33% bar. That is for an X of 4. All right. Does the data in this set look like it's more spread out than the data in the set above? So it may be hard to tell by eye. And that's where the standard deviation will come in handy. It'll tell us mathematically whether it's more spread out or not. So let's calculate that standard deviation now. To do the standard deviation, we want to use the table of the style above here, which is different from the frequency distribution. Here we actually want to list repetitions. So I have to list all the data that appears. Okay, we can calculate a mean for this. Maybe you can tell by the symmetry of the shape that the mean is going to be, yet again, 4. Now let's subtract. We get -4, -1, -1, 0, 0, 0, 1, 1, and 4. After we square these values, we'll get 16, 1, 1, 0, 0, 0, 1, 1, and 16. Now let's compute the sum of that last column. 32 plus 4 is 36. We can now calculate our standard deviation. Numerator will be 36. Now the denominator is n minus 1. But what's our n here? Well, last time it was 5. This time we've actually got 9 data pieces. I get 2.12. So now we know. Mathematically, this data set is on average more spread out than the data set above. The larger the standard deviation, the more spread out the data is.